Oh, welcome back. We've been looking at just the beginning of the chemistry of life. And of course, on anybody's list, when we're looking for what's necessary for life on Earth to take place, first thing that comes to everyone's mind is water. When we look at the planet as a whole, life seems to be concentrated around good supplies of water. And so that's no surprise to us. And so therefore it begs the question, what are those unique properties of water that allow life to exist on Earth? So in this podcast, that's what we're going to focus upon. Now, there is a very special type of bond that life depends on, known as hydrogen bonds. And we want to focus on that and the properties that it creates as well. We've already observed that water is a polar molecule. In other words, the distribution of electric charges over the surface of the water molecule is not even. There are some regions, as you can see here, that are negative, and there are some over here where the hydrogen bonds are located, where the hydrogen atoms are located, that has an overall positive charge. There's a relatively high concentration of electrons on this side of the molecule, and there's a relative lack of electrons on this side of the molecule. And so it's going to have a polar arrangement of those electric charges. And they're very slight, and so therefore hydrogen bonds are relatively weak, but they are still significant. Although they are easily broken, they still play a key role in how water interacts with all the other kinds of molecules and elements that we find on the Earth. And it goes without saying, but I must state it, is that non-polar molecules don't have these same charge regions. There are many other molecules that we'll look at in the near future that have a relatively even distribution of electrons, a relatively even distribution of charge, and so they're not going to act the same way as water does, and furthermore, they're not going to interact with water in the same way that many other molecules do. So water is a polar molecule, all right? You better write this down because it's something important and you're going to see its effects again and again. Well, what exactly does that produce in water molecules? We'll get to that in a moment. Keep in mind that hydrogen bonds, like it says here, form very slightly positive hydrogen atoms and slightly negative atoms as well. Okay, now, what are the three important properties that we see in water molecules? First, a very high specific heat, and that means that water is able to store large amounts of heat because of how water molecules are going to interact with each other. That just goes to underscore that water can store tremendous amounts of heat, and that's going to carry that heat through the ocean currents, such as the Gulf Stream that goes in a northeasterly fashion across the eastern border of the United States. That's going to carry a tremendous amount of heat energy and circulate that and impact climates that are even 1,000 miles from this location. And of course, that occurs in the southern hemisphere as well. And so water has a very high specific heat, and this is what allows you and I to maintain a relatively stable body temperature, as well as all other warm-blooded animals such as birds and all other mammals. Secondly, we see a force known as cohesion. And cohesion is an attractive force that's between like molecules. For example, cohesive forces occur between water molecules and other water molecules. They're going to occur, as we see in a moment, between mercury atoms and other mercury atoms. It also produces adhesion, which is between unlike or dissimilar molecules. And I'll show you the effects of that in a moment. Okay, so cohesion is between like, and when I think of adhesion, I think of adhesive tape. You know, it sticks to just about anything, even things that are very different from each other. Okay, now take a look at these two test tubes. Here we have colored water, and here we have adhesive forces. I'm going to put a letter A here. Adhesive forces are being demonstrated here because water and glass are very different molecules, and yet they're going to be attracted to each other, and water's producing that through these hydrogen bonds. Over here, where we have a test tube of mercury, mercury has very strong cohesive forces, so mercury atoms are very strongly attracted to one another, and they're not attracted to the glass tubing, and so you can see the meniscus, this curved surface, is going to rise up in the center, very unlike what we see on, in our glass of beverages at home. So these are three important forces, three important properties, rather, that are going to play a role in many, many different aspects of molecules, and that's going to impact how even water is going to move from the roots of a plant all the way through its leaves, because it's going to attract right up these very little tube structures that we're going to see. And the second property that I want to focus on right now is the fact that water is able to dissolve many, many substances into itself. And what is formed is what we call a solution. There are many kinds of substances that can dissolve into water, and therefore we often refer to this as a versatile solvent. Jot that down. That's going to be a keystone term that you're likely to see. Versatile means that water is able to dissolve many, many kinds of different substances. Keep in mind, what we mean by a solution is that it's a homogeneous mixture. In other words, if something is a true solution, you don't need to shake it up. It's all the particles that are dissolved are evenly distributed throughout that mixture. The solvent is that which dissolves something else, and water would be the example here. And the solute is that which is being dissolved in the solvent. In other words, these particles are being scattered. That's what we mean by dissolve, is to be scattered and evenly spread apart. All right, and you see an illustration of that right here. In any solution that you look at, we have the solute particles, and they're going to be evenly pulled apart by the solvent. There are many kinds of solutions, but water is a versatile solvent. And again, going back to those properties of polar and nonpolar, there are things that dissolve in water very easily because they have an uneven distribution of charge, or they are charged particles themselves. So polar and electrically charged particles such as ions, they're going to dissolve relatively easy in water. Okay, so polar solvents are going to dissolve polar solutes. And just the opposite is also true. Non-polar solvents, for example, such as nail polish remover, they're going to dissolve those things which are non-polar. And normally, you're not going to see these two be able to mix together with the help of a third kind of molecule. Polar substances and non-polar substances generally are going to remain separate. You could probably think of the last time that you had a type of salad dressing that you had to shake up, and you would see that the vinegar solution in that salad dressing settled to the bottom and the oil settled to the top. Well, that's just one of many illustrations that would bear this point out. As well, water has a property, because it can dissolve those particles that are charged. It can form things that we call acids, and the opposites of acids we refer to as bases. So let's take a look for a moment at how those kinds of things are described. Acids release what we refer to as a hydrogen ion, so they have a positive charge, okay? Positive charge for all the hydrogen ions, and as they dissolve, they're going to increase the concentration there. They're going to make something more acidic. So whenever you have something with a lot of hydrogen ions floating around, that's going to be an acid, and there are particular characteristics of those. When we look at the pH scale, that means the number is going to drop. pH measures the hydrogen ion concentration in a strange sort of way. We won't go into the math in this podcast, but the more acidic something is, the more strong of an acid it is. So typically, pHs between 1 and 3 are going to be what we associate with what we find in your stomach. Very strong acids, such as hydrochloric acid, hydrofluoric acid, they're going to have a very low pH. And those that are not so strong, such as citric acid that we find in our fruits, they're going to be a little bit higher, closer to the neutral mark here. I want to remind you, when you think about things that are acidic, something like citric acid that's found in citrus fruits like oranges and lemons, they have a typically sour taste, right? And maybe that will help you remember that. So acids are sour. Like the last time you got sick to your stomach, your mouth tasted very sour, didn't it? Well, in the same token, bases also have a typical taste. Not the opposite of sour is not sweet. It's actually a bitter taste. Okay? Think of the last time that you got soap or shampoo in your mouth. That's a bitter taste, okay? And so what these substances do is they remove those hydrogen ions. They lower the hydrogen ion concentration, and it's going to cause the pH to come back up. And the reason why, if you think about the water molecule, it's made out of a hydrogen, an oxygen, and another hydrogen. Well, if we take this hydrogen over here, and we bond it to this other molecule known as a hydroxide ion, we get water, don't we? So if we add these kinds of compounds in, it's going to bind to this hydrogen atom and it's going to remove it, convert it back into water. And of course, there's an equilibrium that exists in any type of solution, but this is typically the pattern of reaction that we see. And so on the high end of the pH scale, we find bases. So you're going to find things like ammonia solution, shampoos, soaps are going to be up in this region. Those are the ones that you'll more commonly recognize. A very strong kind of substance would be sodium hydroxide, which is found in drain cleaner in many respects. Okay. Also can cause chemical burns the same way that acids can. They're going to dry your skin out very severely. Okay, so very low hydrogen ion concentration, we get a base. Very high hydrogen ion concentration, we get an acid. Acids are sour and bases are bitter. And all these things are going to enter into the interactions that we find in living things. And they're also very sensitive to these kinds of things as well, both internally and on the outside. Water, perfectly neutral water with nothing in it, is going to have a pH of 7. Okay, so that's right dead middle, in the middle of the pH scale. So we're going to call that neutral. Okay? All right, thanks for watching. Bye-bye.